Oh wait, but that was the
Okay, so we did UDU or variable replacement, or change of variable, I should say, with indefinite integrals. Today we're going to talk about definite integrals, and I think a couple of these showed up on the homework last night, which is why I wanted to do this right away. There are two different ways to solve these types of problems. I'm going to show you both. I think what will happen is you're going to like the first method, but I do need to show you both situations in case a problem pops up where you need to do the other one. Okay, so we're going to start the problem just like an indefinite integral. I got to pick a u, I go through the whole process, and I do that fun stuff. So what do you think u is? Okay. So du is equal to 2x dx. So dx is equal to 1 over 2x times du. Doing a little substitution over here. This becomes u cubed. The x there cancels with the x there. I end up with a 1/2 out in front, and I end up with a du. Notice I didn't write the limits of integration here, because I'm going to wait a little bit on it. My limits of integration are no longer from 0 to 1 because I introduced a new variable, which is u. Okay, and this is where we deviate between the two different methods. I'll show you what the method I prefer, and then we'll come back and do the problem again, showing you the other method. Neither one is more correct, or it's just a matter of how you want to do it. Okay, so I kind of pretend there's no limits of integration right there for now, and I solve this. So 1/2 times 1/4 u to the 4th. Good? Right. Notice no plus c. Why? Definite integral, correct. Now I do my clean it up, meaning multiply the numbers together and do my u substitution. So 1/8 x squared plus 1 to the 4th. Now I'm going to introduce my limits of integration, because now I'm working with x again. Those limits of integration are based on the variable being x. When I'm working with u, it's not x, so therefore I don't have those limits of integration. Okay, so then go through and solve the problem. Plug in 1, we get 1 squared is 1, 2 to the 4th is 16.
Yeah.
16 times an eighth is 2, minus 0 is 1/8. I think I'm doing that correct. So we get 15/8 as a final answer. Okay? I think, hey Tom.
How do you know if you subtract and you add them?
Say again, I'm sorry.
How do you know, do you always subtract them?
Always subtract, fundamental theorem of calculus. Okay.
So it's
Olivia, what do you got?
Where'd the X go?
Where did the x go?
Oh, okay.
Okay.
Wait, can you go back to where you did like 2 next?
Where'd I get the 2 from?
Yeah, I know.
Plugged in 1.
Oh, okay, good.
Yeah.
Okay.
And then I got the 1/8 by plugging in 0.
Okay.
Okay?
Okay.
Any other problems? Okay, good. That's method number 1. And I think that's the method that most of you are going to use. You have to remember that these limits of integration are based on the variable x. And so you cannot use these limits of integration until you put x back into the problem. Gotcha.
So it's basically like what we've done before.
Yeah. Yeah. Except again, you got to remember to put x back into the equation.
Okay.
Okay, now the second method does the exact same thing, but when I get to this second step, 1/2 times the integral of u cubed du, over here on the side I'm going to do a quick calculation. If x equals 1, then u equals, and if x equals 0, then u equals. I'm changing my limits of integration here. Okay. So, if x equals 1, what does u equal?
2.
Why? Who said 2?
1 squared plus 1 is 2.
Yeah, I plug 1 into this because here's my substitution equation. Plug in 1 here, and you get 2. And when x equals 0, u equals 1. And now we generate new limits of integration.
How did you pick those?
My old limits of integration were 1 and 0.
Yeah.
So I asked a simple question. If x is 1, what would u be? And it comes from plugging it in here.
Oh,
If x is 0, what's u? We'll plug 0 in there and you get 1.
you still have to do the f of b minus f of a or whatever.
Yep, still have to solve the problem, but what I don't have to do is the step where I sub back in for x. So I'll finish the problem. I take the antiderivative, I get 1/4 u to the 4th. But now I'm just going to sub right in for 2 and 1. Okay, so 2 to the 4th is, we did this already, didn't we? Yeah, 2 to the 4th is 16 times an eighth is 2. And 1 to the 4th is 1, and minus an eighth. And oh, look, we get the same answer. Yeah.
Is there any like point where we have to use that?
There probably will be a point where you have to, in fact, I can think of an example right off the bat where you have to use that. It's not, you can get by very well just using the first method, but you should also understand and be able to apply the second.
Wait, when do we have to use like the second method over the first one?
You'll see like the problem that you asked me about, problem 113. You explain that using this u substitution and changing the limits of integration.
Oh, okay.
Can you do number 113?
I will. Mason.
What would the first method be called compared to the name of the second method?
Oh, I don't have names for them.
So,
And I don't even know which one is more acceptable in the calculus world. I just wanted to show you both. I like this method better because then I don't have to do this extra calculation here, but I do have to do the extra step of subbing it back in. Either one is correct. It doesn't matter because notice we get the same answer. What won't work, I see your hand, hold on. What won't work is that if I stop here and all of a sudden start doing from 1 to 0, that's going to cause some problems. That's bad. You can't do that. Remember, the limits of integration are tied to the variable that you're working with. Okay? Fine.
I'm confused. What's the difference other than using the extra step that you do? What's the difference between?
Nothing, just different limits of integration. This calculation tells me what my new limits of integration are. That's all. Okay. Anything else? We good on this? Good. That's all I had for you then. Let me stop this.